build up on what we said and see how it is possible to which extent it is possible to generalize what we have in the case of the unitary ensemble to the case of the orthogonal ensemble, where things are slightly, in quotation marks, slightly different. So the orthogonal ensemble is the case, just to make a connection with what is said before, is the case where beta is equal to 1 in the partition function. And the partition function, the tau function, is what I will consider in this in relation to the orthogonal ensemble is the sequence of the partition functions, okay? But we restrict ourselves to the case to the entries of the sequence carrying an even index, okay? So tau to n, okay, where n is a natural number. So we are interested in this object here, and apart from this change, the notation, the expression of the partition function is the same. Okay, so integral over R2, and now we have the modulus of the van der Monde determinant, and the product where I goes from 1 to n of rho zi t dzi, where rho is defined in the usual way, exponential of minus z squared divided by 2 times the sum I over k larger or equal than 1 tk z to the power k. Okay, the only difference is that it turns out to be relevant is that we don't have the square of the van der Monde determinant, we just have the modulus of the van der Monde determinant, okay, to the power 1. Oh, yes. Yes, that's right, thank you. And also here, to n. Yeah. Zi. So, all right, so in this, what we want to do, we want to work similarly to the unitary ensemble. What we want to do, we want to derive have a formula that expresses expressing the tau function in terms of the moments matrix. Okay, what is the analog of the moments matrix in this case? That's the definition we use in the case of the unitary ensemble, where the scalar product is induced by this weight, or we need something different. Adler and Moerbeke proved that you need something different, and that's what I'm going to define now. So let's define this Q-symmetric scalar product So this Q-symmetric scalar product, so if I give you, say, a function of x, f of x, and a function g of y, okay, to this to distinguish it from the scalar product, the standard scalar product, I use this angle brackets, okay, and this is defined. So this is equal to the scalar minus the scalar product of g of y f of x, and this is defined. This is defined as the 1/2 the integral over r squared. Okay, not an integral. It's not a one-dimensional integral. It's a two-dimensional integral. F of x g y. The sign of y minus x times rho xt rho yt dx dy. Okay, so the scalar product, so the skew symmetry is induced by this sign here. So we got the product f of x g of y, the sign of y minus x times rho calculated on x, rho calculated on y in the x and dy. So, and then we have, with this definition of a skew-symmetric scalar product, Adler and van Moerbeke could prove the analog of the result is analog to the unitary case, where tau to n is equal to the Pfaffian of the matrix M, the moments matrix M to n. Okay, so the Pfaffian of A is the square root of the determinant of A, where A is even order skew symmetric. And indeed, so M, the matrix moments, M to n of t, is defined as, is the matrix whose entries are of the form x to the power y, to the power I, y to the power j, scalar product, where I and j runs from 0 to 2n minus 1. Okay, I hope I defined everything here. So the moments matrix now is defined with respect to the skew-symmetric scalar product. So the moments matrix is a skew-symmetric matrix of even order, okay, by definition. And then it makes sense to calculate the Pfaffian, which is the square root of the determinant. Okay, so the determinant of a skew-symmetric matrix of even order is a perfect square, and you define the Pfaffian in this way. Okay, so now given the matrix, this skew-symmetric analog of the moments matrix, we can consider the semi-infinite extension. We can consider the semi-infinite extension, and then we have s to the minus 1. We consider the factorization, okay, s to the minus 1 times j, s to the minus 1 transposed, where j is 2 by 2 block diagonal, and such that, so the transposition of j is minus j, and j squared is minus the identity. Okay, so just essentially the matrix is block is like this. And then it continues. Okay, so the matrix J, just to clarify, as 2 by 2 block diagonal with of that form, and then it's 0 everywhere else. All right, so now we can state what is the analog of the theorem. So here the detail become a bit more intricate, but the logic is slightly more intricate, but the logic is essentially the same. So what I need to do is to consider the derivation of the Toda lattice equation relies on the splitting of the algebra. Okay, and in this case, we consider the splitting. Okay, I use this notation, this kind of curly, like T and curly N, okay, to define the splitting, the algebra splitting, where this projection, this T projection, are lower triangular matrices. I just realized that I forgot to say what in the factorization of M infinity, so S are lower triangular, okay, as before, lower triangular. So the matrix S is the lower triangular, okay, and J is is defined over there. So now let's consider the following splitting, algebra splitting. So T, the lower triangular, the projection T is the lower triangular matrices of the form. So let me just make it very explicit. So we have so of the form the matrix Q. Okay, let's call this matrix Q has entries on the diagonal. We have 2 by 2 block diagonals of this form. We have at some point, say, Q 2n 2n, and then it replicates Q 2n 2n 0 in 0. And then we got the next one would be Q 2n plus 1, Q 2n plus 1, 0 in 0. And then we get something here, which is non-zero. The lower triangular 2 by 2 block lower triangular part is contains something, and then it's the upper 2 by 2 block diagonal is 0, right? So this matrix continues. So T comprises the 2 by 2 block lower triangular matrices, where the main diagonal is made of 2 by 2 blocks, where in each block you replicate the element, say Q2n to n, Q2n to n on the diagonal, and then 0 on the off diagonal part, and then you got 0 on the upper triangular part and non-zero in the lower triangular part. These are these are semi-infinite. Yeah, yes. Still semi-infinite. And then we get n, this component n is given by the symplectic matrices. Okay, so these are the matrices B such that J transpose is equal to B. Okay. Now, given a matrix A, we want to define, okay, given a matrix A, we want to define how we calculate this T component, respectively, and the N component. So given a matrix A, is its projection T is written explicitly as A minus J A plus transposed J plus 1 over 2 A0 minus J A transpose 0 J, and then AN, the component AN is A plus J A transposed plus J plus 1 over 2, and A0 plus J A transpose 0 J. Okay, where so the subscript 0 identifies is the 2 by 2 block diagonal part of A, and A plus or minus is the 2 by 2 upper or lower block diagonal part of A. Okay, so this is the definition. So how do we, okay, this is a bit, it's a kind of non-trivial analog of what we had before. So, but this gives us a clear way of calculating this projection. So I've got a matrix A. You take the 2 by 2, extract the 2 by 2 block diagonal, and this is A0. And then you extract the 2 by 2 upper triangular part, and this is A plus, the 2 by 2 lower triangular part, and this is A minus. You stick them into here, and you can calculate the two parts of this, the elements of this algebra splitting. So this is necessary, okay, for to define allows us to state the problem, the theorem. So what is the theorem, which is the analog? So this is Adler or Rozov van Moerbeke. So 1999. So if you define L, so we got let me remind here, M infinity. M infinity is S minus J S minus transposed, right? So now we have this skew-symmetric version of the moments. We take this factorization, clarified by this, specified by this lower diagonal matrices. You define L as S times lambda S minus 1 of T. Okay? So given L so defined, where lambda is as before the shift operator. So then the derivative of L with respect to Tk the derivative of L with respect to tk is equal to minus L to the power k projection t. Okay, so this particular projection on the algebra splitting commutated with L. Okay, for k, where k is larger or equal than 1. So this is what is called the Pfaffian lattice. Right? This system defines a Pfaffian lattice. So a system of equations is compatible, and and for our purposes, so I mean, clearly this extends, provides us the analog in the orthogonal case, with the difference that this hierarchy tells us how the tau function, how the even sequence of tau functions behave. Okay, the odd sequence is not incorporated in here, so it's not. We don't have this determinant, of course, this determinant formula in the even case. The Pfaffian is not defined, and we don't have an analog of that. So now let's look at what the yes, of course, yeah. Yeah, I can't. So yeah, I can't really comment on why this this symplectic. I think the symplectic structure is more related to the fact that we're working with the even order matrices, and somehow we have that particular structure that. So, and then we have a skew-symmetric form. You know, the scalar product is skew-symmetric. So, despite the character of the random matrix ensembles, we got all the ingredients that make a symplectic structure. And so, yeah, and I don't have any deeper understanding of that apart from the observation that so we got all the right ingredients that to make a symplectic structure. And so we so one of the things we looked at, and this is essentially what I'm going to share in the next 15 minutes, and is the is a result of our recent work with Costanza Benassi and Marta Dell'Atti and myself. So the paper is on the archive and is currently submitted to a journal. So, and where essentially we studied in detail the analog of the Toda lattice and the analog of the thermodynamic of what happens in the thermodynamic limit in the case of the Pfaffian lattice in connection with the orthogonal ensemble, which is very important. So Adler and Moerbeke focused on deriving the equations for the tau function and the equation and the Lax equation, but somehow in their work, the information on the initial condition, which is one of the elements that originally, one of the important elements of the original work of Witten, for example. So here we are combining, we We rely very much on the work of Adler and Moerbeke in terms of the derivation of the integrable system, but we want to inform the analysis of the system through the initial condition. So we need to understand what the initial conditions are in order to write equations that we can hope we can solve. Because we see that the Pfaffian lattice is a much more complex system compared to the Toda lattice, which is not simple by itself. So essentially, the first observation is that, okay, let's look at the structure of the matrix L. So by looking at the structure of the matrix L, the matrix L is of this form. So we have a diagonal. So the first element is 0. Then we have, let me denote the elements in this way. So V01 minus V01, V02 minus V02, and so on. So we have a diagonal in the matrix L. The first entry is 0. Then we got these variables, okay, where I use a notation that tells that tracks, once you fix the diagonal, tracks the position along the diagonal. So in this case, we have V01, and then the next one is minus V01. Then we get V02 minus V02, and so on. Okay, somehow the ones that occupy even positions along the diagonal are alike, and the ones that occupy the odd positions along the diagonal are alike. Why am I doing this? This is important because when we look at the equations, we spell out the equations contained in that form. You see that the form of the equations satisfied by the entries in the even position are of a certain type, and they are very similar. And the ones, apart from, a change of the indices, like a shift in the indices, and then the one sitting in the odd positions along the diagonal satisfy similar equations. So then we have a one-upper diagonal. So we got the first element is 1, then we got another element that I call W01, then W01, then you get again 1, and then W02, upper index and lower index. So, and so on. So 1 and so on. So the upper diagonal is also particularly simple because the odd positions, in the odd positions is constant, is always 1, and the even position are denoted like this. So W0 is the first diagonal, upper diagonal, and actually the first diagonal at all because everything up above it is equal to 0. Okay, so this is the first non-zero diagonal. Everything else above it is 0. So what happens below? So the first lower diagonal is of this type. So W minus 1, 1, then you get W1, 1, then you get W minus 1, 2, W1, 2, and so on. You see, the upper index now starts counting the diagonal, and the lower index the position along the diagonal. So the first lower diagonal has upper index plus 1 or minus 1. Minus 1 corresponds to the odd positions, and plus 1 to the even positions. So essentially, W minus 1, 1, W minus 1, 2, and so on are alike, as well as W1, 1, W1, 2, and so on are also alike. We have two groups of entries. The ones given a diagonal, the ones living in the even positions, and the ones living in the odd positions, and so on. This now we get W minus 2, 1, W2, 1, W minus 2, 2, W2, 2, and so on. Okay, and then we got stuff here. So the lower triangular part is all filled with elements. Okay, so we have essentially two groups of variables. The ones sitting in the even diagonals, okay, starting from the upper one. So this group, and no, sorry, this is V. This is V, this is V, this is V. Okay, so we alternate the W here, then skip W here, skip W here, and so on. And then we get the V's starting from the diagonal, then skip, then we got the V's, and so on. Once you select a diagonal, you have even, just need to distinguish even positions and odd positions. We get these two groups of variables, actually four groups: even diagonals, and even diagonals, odd diagonals, even position on a diagonal, odd positions in a diagonal. All right. So essentially, if you look at, if you zoom a cell, you will have an element. A 2 by 2 cell will be of this form: minus W minus K1, V K minus 1N, V minus Kn, W Kn, right? So a generic cell in the bulk will be of this form, if you like. Okay? So yeah, it looks like very non-intuitive, but when you look at the equations, and I will explain why, it would probably be clearer. So now there's a question: how do we express the W's in V, this variable, in terms of the tau function? Now, there is not a simple formula to do that in general. We have nice formulas for the first elements, W0 n, right? This is the square root of tau, very similar, essentially the analog of this is the analog of the B's, the upper diagonal in the Lux matrix for the unitary ensemble. And then we have V0n, which is the analog of the, so we got the log of tau to n derivative with respect to T1. So Adler and Moerbeke derived like a recurrence formula to calculate all the other elements, but it's not explicit. You have to just calculate term by term, each term at every single step. And what happens essentially that you get like the expression is some differential expression. The expression is given by the application of some operator that can be somehow expressed in a compact way using elementary Schur polynomials, but still we don't have like a simple compact expression for the generic element. So if we want to calculate these elements at the initial time for t equal to 0, we need some we need some different approach, okay? And this is the first thing I want to show in this, in the next step. So, and what we want to do first is to construct a particular reduction, right? So the first observation is so V0n calculated at 0 is equal to 0. Okay, for similar argument. So you have you're integrating an odd function and it is equal to 0. And actually for these, okay, for all plus minus kn calculated at 0, by looking at the recursion formula, from Adler and Moerbeke, you actually realize that all these entries involve an odd number of derivatives, which gives you an odd function, and then if you calculate it for t equal to 0, these are all 0. Okay? So, and then the idea is to consider a particular reduction. So the particular reduction where the matrix L, okay, where the matrix, we assume that the matrix L preserves the structure of the initial condition. What we can tell about the initial condition is that on the diagonal, all the V's, okay, all the V's are 0. So we have zeros along, so the first diagonal. Then you got 1, W0, 1, and then 1, W0, 2, and so on. So then we get the second lower diagonal is W minus 1, 1, W1, 1, and so on, and then all zeros, okay? And all zeros on the upper diagonal part. So essentially we consider a reduction where the matrix L, we assume that the matrix L preserves this structure of the initial condition. So all the entries, the diagonal that are 0, corresponding to the V variables, are 0 at any time, and then the other ones can depend on T. So now the question is, what is the reduction of the Pfaffian lattice that is compatible with this constraint? This would be the analog of the Volterra reduction I mentioned before. So this reduction, okay, corresponds to the choice of the vector of times, where similarly to what you would do to get the Volterra reduction, you choose the times of odd index to be equal to 0. Okay, you vary only T2, T4, T6, and so on. Okay, you fix all the odd times equal to 0. Okay, so then we have this theorem that we proved in our paper, made of two parts. So the first one is that the equation of Wkn with respect to T2. So what we do is we look at the first equation of the Pfaffian hierarchy. Okay, now we concentrate on the first equation. This is equal to some function W13, which contains W10, W0, W1, Wk, plus some function, I call it capital W2, function of W0, Wk, plus or minus 1. So, what is W3? W3 is a homogeneous polynomial of degree 3 in these variables. So I specified only the upper indices, 0, 1, k, and this involves all lower indices. I don't specify them just for shortness. It's a function of 3 variables. It couples, yeah, for each k, what couples are, imagine in this matrix W0, okay, we got W0, W1, the upper indices. It couples the entries W0, W1, and then the kth entry, not the ones in the middle. So it's a polynomial of degree t in 3 in these variables. And then this one is, again, an homogeneous polynomial of degree 2. We actually W0. It's understood in here. It couples different entries. Now, okay, we'll be clear. I'm writing this way because the actual system is quite long. Will take me a long time to write. But for example, yes, finite. Only finite many terms. There are no. It's a proper polynomial. Yeah, and for example, just to give you a clearer idea, so the derivative of W0n. So the first equation is W0n divided by 2 times W0n plus 1, W1n plus 1 minus W0n minus 1, W1n minus 1 plus W0n, W minus 1, n plus 1 minus W minus 1, 0. Okay, for example, the first equation is, you see, it contains three nearest neighbors. Okay, it's up to two nearest neighbors. So in relation to Wn. Okay, so and you see that it contains W0 and W1. So if you increase the upper index, what happens is that the equation involves the index of interest, K, and then always W0 and W1. So the first elements of the chain. And then what we proved is this is the first part that tells us what the equations are. And now the question is, what is the initial condition? Okay, what are the initial conditions associated to this? And so the second part of the theorem, okay, tells us that W minus Kn 0 is equal to 0 for minus K less than minus 2. Okay, and W minus 1n 0 is equal to 1 over 2, and W minus 2n 0 is minus W0 n equal to minus 1 over 2, the square root of 2n minus 1. And then we get Wkn 0 calculated explicitly. So 2 to the power k plus 1, k plus n minus 1 factorial divided by n minus 1 factorial times 2n minus 2 factorial divided by 2k plus 2n minus 2 factorial, okay, to the power 1 over 2 for k greater than 0. Okay, so this gives us the complete information on the initial condition associated to that system of equations. So how do we prove this? I will just say this in words because it will take a long time to prove it, but to state it explicitly. But essentially, the idea is that similarly to the case of the unitary ensemble, the eigenfunctions of the Lax operator, the Lax matrix, are skew orthogonal polynomials. So you use the skew orthogonal, symmetric scalar product to define the skew orthogonal polynomials. The skew orthogonal polynomials are the eigenfunctions of this Lax operator. And in a separate work, Adler, Van Moerbeke, Forrester, and somebody else, which in Nagao, yeah, proved that you can map skew orthogonal polynomials into orthogonal polynomials. So essentially, if you write down the eigenvalue problem for the Lax matrix on the space of the skew orthogonal polynomial, you can map the skew orthogonal into the orthogonal polynomials, and then use the projections on the orthogonal polynomials to single out the entries of the matrix L. The thing is that it's easy to do it for t equal to 0 because the orthogonal polynomials associated to the skew orthogonal set here are the Hermite polynomials. So we can calculate everything explicitly. And this gives us yields these formulas for the entries. Okay, they just come out from the Hermite polynomials combined with this map provided by Adler, Forrester, Nagao, and Moerbeke, this map from the skew orthogonal to the orthogonal. So this gives us the complete information on the initial condition, and now we can do two things. Of course, we can use these initial conditions as you would do in the case of the unitary ensemble to understand, okay, what are the scaling properties of what kind of expansion I have to consider for the W's to perform the continuum limit when I send n to infinity, or you can alternatively use the information on the initial condition to further reduce the complexity of that system of equations. So I'll probably do this second thing, and state, at least in words, what would happen in the thermodynamic limit. So you see a further step you can work out is the following. Look, so according to the initial conditions, for all negative super index k, for at the top, all those entries are 0 at the initial time. So then we can say, okay, what if they were constantly 0? Okay, so we assume that they are. We reduce the system, assuming that they are all 0, and we assume that the entries, the W1 minus 1, are constant, equal to a half, and they are the same for any index n. So what if we assume that this property is preserved in T? Okay, so we can prove the following theorem. So this is also in our paper, and you assume that for all k positive, so W minus kt is equal to 0, identically equal to 0. W minus 1n is identically equal to not identically equal to 0, does not depend on n. Okay, we don't say that it is equal to a half always. We just say that it does not depend on in the index n. We know it's a half at the initial time, but not necessarily at all times. So then, what we can prove is that W0 n t is equal to minus W minus 2n t, and this is equal to some constant W minus 1 t, where the constant Cn is the square root of 2n minus 1. So if you impose this assumption, okay, and you use this assumption into the equations to which W satisfy. So what we get as a consequence is that W0, the upper script 0 and minus 2 are essentially the same up to a minus sign. They are the same to W minus 1. And then what we're left with is a further property. So we continue here. So WKNT. So for the other K, did I specify the Ks? Right. So yeah, K, positive K, yes. So positive K, so the negative superscript. So, and then for K positive, for positive upper index, WKN can be expressed in terms of the first element of the chain. So we got a binomial CL divided by Cn plus K minus L, WK1. So we see that this assumption here gives us lots of simplifications, some algebraic dependence, functional dependence between the first entries in the chain, and then this is very important because if you fix K positive, the nth element can be just expressed in terms of the first. So now what we get as a result, what is the final result, is an equation for the first elements. So set I call, say, capital W minus 1 equal to W minus 1, capital WK equal to WK1 divided by some function f, some constant Fk. So 2k k factorial divided by square root of 2k factorial. And okay, we got these two variables. Just the first is just itself, the same W minus 1. The second is WK1, so the first element, just scaled by a constant. And then we have this system of equations. So derivative of W capital W minus 1 equal to 2 times W capital minus 1 squared, capital W1, and then we get W K d by d2 equal to 2 times W minus 1 times K plus 1, W K plus 1 minus W1 WK minus K minus 1 WK minus 1. So essentially we started from a two-dimensional chain where W has two indices, K and N, and then with this further assumption allows us to reduce the two-dimensional chain to a one-dimensional chain that is fully compatible with this with the initial condition prescribed by the model. So I see this as a progress because we have now the solution we look for. Yes, it's a solution to a reduced Pfaffian lattice, which is a two-dimensional lattice, but this further assumption tells us that we can describe that solution as a solution to a one-dimensional chain. And this is the chain. So we got the equation for W1 and then all the WK. Okay, and the coupling is of this form. We have a quadratic coupling. So yeah, up to a cubic coupling. So this chain, I couldn't find it anywhere in the literature, so I don't know anything about this chain. I know that it must be integral because it comes as a natural reduction of an integrable system, this Pfaffian lattice, but I've never seen it anywhere. I don't know yet if there is what is its Hamiltonian structure and so on. Okay, so it's allegedly a new integrable system that arises as a reduction of the Pfaffian lattice induced by the particular the form of the solution of the particular solution consistent with the orthogonal ensemble. So a final comment: what about the thermodynamic limit? I'll just say this. I try to express this in words. So for the thermodynamic limit, we do the analog of what you would do in the unitary ensemble case. So you look at the initial condition and you see what is the right scaling to obtain something meaningful in the thermodynamic limit. In the Toda case, we have that the expansion is just we can take a Taylor expansion of your degrees of freedom, right? In this case, we see that some W's, so the initial condition has a singular behavior in epsilon. So there are some entries in the singular in the initial condition that, if you write x as epsilon n, will have a behavior, a leading order of the type 1 over epsilon. So some of the entries cannot be like a Taylor series, a Taylor expansion of the interpolation functions cannot be all just a Taylor expansion in epsilon. Some of them have to start from 1 over epsilon. Then you perform this expansion, you get some system in the thermodynamic limit. But what happens that when you take this expansion, the leading order is not a closed system. There is a resonance with the next to the leading order constraint. But there is a particular choice of a function taken from the next to the leading order that is consistent with the initial condition. It closes the system at the leading order. So you can make a particular choice on the next to the leading order contribution that is out of control to close the system at the leading order. And now the thing is that what you get when you close the system at the leading order, you get, for the leading order asymptotics, you get this very same equations, which is something that I found very surprising. But this system of equations survives for the leading order in the thermodynamic limit. And there is a quite non-trivial thing, because this expansion is secular, right? There is this resonance with a higher order term, which doesn't occur when you do the interpolation of Toda. And then we look at the system, it's a non-homogeneous term. We make a choice that is natural because it's compatible with the initial condition. And then what you end up is the very same system of equations. Okay, so this is something, it must be the case. There's probably a reason why it must be the case, and I don't see it, but it's, it's a nice coincidence, an interesting coincidence. So thanks very much for your attention, and I'll probably stop here.